Okay, welcome everyone. The next talk is about reverse engineering of the MOS 6502 CPU that was designed for the Apple II, the NES, or the C64. And I hand you over to Michael Steil, who will present you everything. Thank you.
Hello. As you just heard, the name of my talk is Reverse Engineering of the MOS 6502 CPU. My name is Michael Steil, Michael Steele. Fans, yay. Subtitle is 3,510 transistors in 60 minutes. Let me just get some quick overview of the audience. Who of you has written any assembly code ever, any architecture? Whoa. Okay. Who has not written, who doesn't know what assembly is? Okay, that's good. That's useful. Who has written 6502 assembly before? Okay, so don't feel bored in the first 10 minutes. Who has ever implemented a 6502 emulator or re-implemented 6502 in an FPGA? 1, 2, 3, 4. Okay. Who has been part of the original design team of the 6502 in Pennsylvania? Okay. No liars in this audience. Okay. So for all those who don't know about the history or don't know about all these things about the 6502, there was this company MOS, which was founded in 1974, all by people who quit Motorola, who had been working on the 6800. This team was based around Chuck Peedle, who led the team. And in 1975, they introduced the 6502 on the market, and it was used in many computers, like you can see Steve Jobs and Steve Wozniak here. Was a very popular CPU. Which got used in all of these. The Apple I, the Apple II, the BBC Micro, all the Commodore series, all the Atari 8-bits, the gaming consoles, and the Atari system, the Nintendo Entertainment System, the Super Nintendo, and of course, Bender and Flexo. Not to forget also the T800 Terminator series. So what makes the 6502 that interesting? Because there's also been other CPUs which were kind of successful, like the Z80. But if you compare them, the 6502 had 60% fewer transistors. It was much more optimized. It wasn't as powerful, but it was even faster. It was more constrained, but it was also more elegant. And some people would say that elegance or perfection comes from simplicity anyway. So my talk consists of 3 parts. Part number 1, the 6502 from top down, meaning a programming model, how you would interact with it, so don't feel bored. Second one, 6502 from the bottom up, meaning how to disassemble a 6502, how to look at the gates, how to take photographs, how to understand what's going on inside at the gate level. And then the third piece is from the inside out, meaning what have we learned from deconstructing the 6502, what do we know about the components, how do they interact, where do all these weird quirks and stuff come from. So, part number 1, 6502 from top down. Whenever you want to start with a new CPU, you would start with some data sheet or something. Let's not do that. Let's just look at code. For all those who haven't seen a 6502 code, let's walk through some instructions here. STA, store, accumulator. You have 3 registers, A, X, Y. JSR, jump to subroutine. This is the call instruction. LDA, load accumulator. Compare. Compares the A register, BCC, branch if carry clear, so it branches if it's slower than the compared value, jump to subroutine again. And then there's the addition instruction. You always have to clear the carry flag before you add, because the carry also gets added if you don't want the extra carry. BEQ, branch equal. So what's also always interesting in this very low level kind of programming is to know how the encoding works. So the opcodes, here the opcode is always 8 bits in size, It's always a 1-byte opcode, and which encodes both the instruction and the addressing mode. And the operand is either 0, 1, or 2 bytes. So a CLC, clear carry, doesn't have an operand, so it's a single byte instruction. And it goes up to 3 bytes for the jump to subroutine, which has a 16-bit address after it. You can see an interesting thing here in the first line already. Store $56. It stores something in memory. Memory is 16 bits, is 16 bits wide, 16 bits addresses. But in this case, because it's in the first page of memory, there's an extra encoding, which makes the instruction shorter and even faster. So from a more theoretical point of view, what's the programming model? You have the A register, the accumulator. It stores everything and it transfers everything. Whenever you handle data, whenever you do arithmetic and logic, it goes through your single A register. And the index registers, which aren't as powerful, they can count up and down and be used as an index in accessing an array, but you cannot do any arithmetic or logic on them. You have the processor status register. It's 8 bits. You have 4 bits in there, which are about arithmetic and logic. 1 bit, which signals its decimal mode. I'll talk about decimal mode later. It's quite boring. And there's 2 more bits about exception and interrupt handling. The program counter is at 16-bit address spaces, so it's a 16-bit program counter. And the stack pointer is also 16 bits. I mean, it has to be an address. But the upper 8 bits are fixed. They're always hard-coded to 1, so the stack pointer register is actually only 8 bits. So this has some implications to the whole programming model here about the address space. 64 kilobytes of address space, and the first 2 pages of 256 bytes each are special. So first page, or the 0th page, is 0 page, goes up to FF, and it's meant for all these addressing modes where if your address falls within the first page in memory, then you have a special encoding, and everything is faster. And there are some things you can only do with 0 page. Because the system is rather register constrained, you only have this accumulator register, 0 page is very useful. And the stack is always constrained to the first page, so stack counts down from 01FF down to 0100. So this rather complicated slide, and it'll get worse, is supposed to give you an overview of all the instructions that exist and how to put them into some order somewhere, and so that you have seen all the memos at some point. So you don't have to, in case you don't know this already, you don't have to remember all these things. There's load instructions. You can load from memory into the accumulator, into X and Y. If you want to store STA, STX, STY into memory, you can transfer it between registers. There are 2 groups of read, modify, write instructions. The shift instructions work with the accumulator or with memory. You can decrement and increment memory, and as well as the index registers, because index you have to count up, you have to count down. And also done by the ALU is addition and subtraction, as well as the Boolean operations. And there's the other 2, which the compare one is basically just a subtraction, but only stores the flags and not the result. And the bit is an AND, only stores the flags, not the results. Speaking about flags, you can set and clear some flags, and you can branch depending on whether flag is set or cleared. So these are the 4 arithmetic and logic bits in the program processor status register. There's also the unconditional jump, and a jump to subroutine and RTS is a function call and function return. And if you want to do a software interrupt, I mean, interrupts work the same way, but there's a software interrupt, break, and return from interrupt, which does the reverse. And for stack, you can only push the A register, as well as the processor status register. And these are all the instructions that exist. So for all the general purpose instructions, these are the addressing modes that can be used in combination with these. There's an immediate addressing mode for using constants, absolute addressing modes, absolute and X and Y indexed. The same always with 0 page, and then 2 special ones for special 0 page stuff, which work around some other deficiencies of the design or some limitations of the design. Let's walk through the more important addressing modes for now. So immediate addressing, you have the hash sign right there. You load a constant in the accumulator, in this case, LDA, load A. So if we do that, we have the constant of 17 in A. Absolute addressing means you have a 16-bit operand there. If you load from 314, we look up in memory at address 314. What we get is a 31, and we have a 31 in A. And then zero-page addressing is this optimization. It's a different encoding. We only have an 8-bit operand. We load from address 2. We look it up in zero-page, and we find a 0. A is 0. Absolute, comma x means absolute plus x. So the x register gets added to the constant pointer that we encode in the instruction stream. So 200 plus x, if x is a in our example, we load from address 20a. We look it up, 20a, that's 52. So we assume that at 200 we just have an array of bytes and x is iterating over those. Absolute comma y, same thing with the y register. They're pretty symmetric. The same exists with zero page, but the interesting thing is here that there's a wraparound inside zero page. So if x in this case is 16 or above, it would wrap around to 0 again, so you cannot exit zero page with this indexing. Same with zero page comma x, comma y. Now there are two more interesting ones, the indirect ones, because as I said, we're register start. We don't even have a 16-bit register at all. So what if you want to use a pointer? If you have a 16-bit pointer, you cannot hold it in a register, unlike on the Z80, for example. So you have to store these pointers in zero page, and you can use zero page as pointers and then use them directly in instructions like this one. This addressing mode, zero page x indexed indirect, means that we assume that at 80 in zero page in this example, we have an array of pointers, and we index the array with x, and then we load from one of these pointers. So what the CPU does, it looks at AC, 8C, because x was C, so it indexes that. It gets the pointer. It's little endian, the correct endianness, as everyone knows, and it loads from that address, C43F, does another lookup, gets the value into A. So it's double indirect, it's slow, takes 5 cycles or 6 cycles or something. Then the same thing, or not the same thing, this is zero page first indirect and then Y index, which is much more useful because this treats 14 and 15 in zero page as a pointer, as a 16-bit pointer. This pointer in this case at 1415 is D800, and then afterwards we add Y of 28, so we read from D8 to 8. So normally whenever you have to count up somewhere and you don't know the pointer, put it in zero page and you can work with that pointer from there. Stack doesn't need much addressing. It's all implicit instructions. Stack works like this. Normally you would initialize it to FF, which is the top of stack. If you push something on the stack, it stores it first and then decrements the stack pointer. Let's do that again. Let's push something, it stores it where the stack pointer points and decrements the stack pointer. So if we pull something, then it increments the stack pointer and then reads from that address. Let's do it again. Increment and read. So this decimal mode is something that I guess you must be a 70s guy or an 80s guy to fully understand decimal mode, or maybe people did financial stuff on their Commodores and Ataris. So decimal mode, BCD, binary coded decimal, is meant to optimize the way you store numbers, integer numbers, which you would print anyway. So in a normal case, if you add 2 to 9, you would get B, hexadecimal B, but if you have decimal mode turned on, then without this being any slow or anything, you will get a result of 11, which is hex 11, which is, I mean, wrong in the binary sense, but from a decimal perspective, this would be the correct answer. So this was all the user mode kind of view. So from a more systems perspective, these vectors are interesting. What happens with interrupts, with reset, and IRQ. There are 3 vectors at the top of the address space for NMI, non-maskable interrupt, for the reset vector, and for the IRQ vector at the very top of memory. We'll talk about these vectors later. That's an interesting thing. So looking at all the instructions that we have and looking at all the addressing modes that we have, if we combine them, if the CPU were completely orthogonal, being able to combine every general purpose operation with every addressing mode, it wouldn't fit into the 256 different opcodes. So what they did with the opcodes is only encode the ones which really make sense, the ones which are most interesting, most important. So only about 60% of the opcode space is used. And the rest is just, well, they say it's undefined. So let's walk real quick through another example here. This is something taken from some random ROM somewhere. You might have seen the code, might have used the code. We load something from 0 page, we compare it against a constant. If it's not that constant, let's jump out. Let's get the high bits, the upper 8 bits. Let's also compare it to a constant. It's not 6502, so let's jump out. Otherwise, we did a subtract there, so we have a 0 in A now, so we store a 0 into 11. We copy the 0 into the Y register. We load an 80 and put it into 12. So at 11 and 12, we now have a pointer of hex 8000. We load an index register of A, which is 10, so we count down 10 from somewhere. We use that index register right there. We load something from ROM, so we index some array counting down from 10. Mask off some bits, store it at that pointer at 8000 plus Y. Increment Y, if there's no overflow, skip the next instruction. Otherwise, increment that 80 that is stored there to 81, and so on. And then count down the X, so the 10 down to 0. Also loop, decrement how many times we want to do it. That's another parameter that we got. Branch and RTS return from subroutine. So you can see the parameters that we got were stored in 11, 12 in 0 page, and in 46 in 0 page. So every time we have to do a lot about the 0 page. Now the question is, what does this code do? So if you have ever used one of the later PET models, the Commodore PETs, if you said this on the command line, a wait instruction is a legitimate instruction. It does interesting stuff. If you use the constant of 6502, it would do that. Now, why is that? That's because, well, Bill Gates wrote it. Commodore licensed Microsoft Basic for the PET, then went back to Microsoft for a bug fix release for later versions of the PET, and Microsoft kind of got pissed because they didn't include the name Microsoft anywhere. It said Commodore Basic. So they just put this Easter egg in. And we're pretty sure that it's really Bill Gates who wrote it, because back at those times, 76, 77, Microsoft had 3 employees, and one of them couldn't code, and the other one did Z80, and yeah. So Bill Gates did write 6502 code at some point. What's interesting about an architecture like that, 8-bit architecture, is that you know the length of your cycles, also about understanding what's actually going on inside, not just about optimization. So every memory access is a single cycle. The whole system is very memory bound, so mostly you only look at how many memory access do you have for executing an instruction, and you know how many cycles it'll take. But there's the special case of every instruction at least takes 2 cycles. If we go through this real quick, load from 0 page takes 3 cycles, because you have the load, you have the operand, and then you have the load from 0 page. The compare has 2, because the instruction is 2 cycles. It doesn't do any other fetch. This one has 2, because it's also a 2-byte instruction. If the branch is taken, there's an extra cycle there. We've had this one. This transfer is only a single byte, but we have a minimum of 2 cycles. Then this one is interesting. The load, the operand 1, operand 2, that's 3 fetches already. Then the actual fetch from memory, so that's 4. But in case we have an overflow, in case we have a carry into the E1 page in here, then the ALU has to do 1 extra step, so that's 5 instructions. And let's go through all these real quick. So 6 for something more complicated. An increment of 0 page is 5. And what can really kill performance is an RTS, or a jump to subroutine, and an RTS in a combination are already 12 cycles that you're wasting right there. So the 6502 has some weird things about it. Some you could consider bugs, some just, well, you don't care, but why do they happen? So for example, if you increment something in memory, what you would expect is you read it, you write it. But what happens is it reads it, it writes back the original value, sometimes within those 4 cycles, or 6 cycles, and then it stores the new value. So from a software perspective, you cannot see the difference. But from a hardware perspective, you can measure that. And you can build a computer around that, and you can make use of that oddity and build your copy protections or obfuscation around things like this. This one is a real bug. If you have a break instruction, I mean, you wouldn't have it in real code, but in a debugger, you normally use it for debugging, and you put your break in if you want to know where your code went. But if you have a break in real code and an interrupt happens at the same time, then your break will just get lost. The break will not be done, just the interrupt will be handled. And there's this one big question mark here about illegal opcodes. this is the one thing that so many people have looked into. What happens if we use all these other opcodes? What if we just put a 2 into the instruction stream? What happens to the CPU? Does it crash? Does it do nothing? Does it do something useful, useless? The answer is all of the above, depending on what you use. Many people have done a lot of research on that and compiled these tables. If you use that opcode, most of them don't really make all that much sense. It's mostly a combination of other things. Some do make sense. So another question is, how can we find out what exactly is going on without just describing what we measured? So we have to go from bottom up. We have to understand from a transistor level what's going on inside the CPU. So part 2, from bottom up. So if we want to dive into the inner workings of a CPU, we could look at data sheets, but yeah, we get something like pinouts. We can also get something like timing diagrams. They tell us something about what's going on. So the original documentation back in those days wasn't that bad. You can also get schematic diagrams or block diagrams like this one, but this particular one is neither useful nor correct. Because, for example, there's this one internal bus, but there's no internal bus. There's actually 2 internal buses, and that's a very important difference. What we can find is some other timing diagrams. For example, if you have an absolute indexed instruction, what happens in every single cycle? That's useful, but still doesn't really tell us what's going on, especially with illegal opcodes or anything like that. So what can we do? Where can we get the extra information? We could like dive down from up and just ask someone, ask that company. Maybe you have some more documentation. Well, we cannot really ask them because they got bought by Commodore in 1976. MOS doesn't exist or hasn't existed for a very long time. What's interesting, Commodore never changed the markings on the chip at least until 1990 or so, until they finally switched to Commodore Semiconductor Group, CSG. So most MOS chips you will find will actually say MOS still. But Commodore themselves got bankrupt in 1994. Then ASCOM bought them. GMT Microelectronics got some of the fabs. ASCOM was a retailer, a German retailer, which also got bankrupt in 95. Viscorp was supposed to buy some stuff. Gateway bought all the Amiga IP and all the Commodore IP. Comtech bought all the retail business. Gateway then spun off a company, and they renamed themselves. So Commodore is out there somewhere, and someone is working on the Amiga OS. The source code of that is already there, but who would you really ask about, or who would you contact about getting more information about that? Well, you could contact the original designers. You could do that, but the problem there is we cannot really ask them, so do you maybe have another DVD, floppy disk, paper tape, punch card or something? They didn't have any of that because 6502 and all the CPUs from that time were designed completely by hand. There were no computers involved. So what you can see here is 2 layout engineers cutting rubylith, that's some kind of plastic foil, cutting the actual mask that was later used, that was later shrunk to about a square millimeter and used to burn those processors. So people wouldn't probably have copies of these big sheets. But some of this documentation, some of this stuff might still exist. So in 95, something showed up. Someone wrote a paper about something, I don't know. And it had this nice sheet. It said it's some original schematic diagram from the 6502. He doesn't say how he got it, but it looks really good. It's either really nicely reverse engineered or it's an original. If we have a quick look at it, we can see there's a lot of program counter logic. It's rather detailed, so you can see a lot of what's going on. Not all of it makes sense. So by just looking at this, you wouldn't really know what's going on yet. But that means that it probably is done by someone who knew a lot about it. So cycle counting goes on here. The opcode is stored in the instruction register and then forwarded to the Decoder ROM. And we have the registers here. There are the 2 buses, the D bus and the S bus, which connect the different registers to the ALU, and this is the ALU. What also surfaced just recently is a couple of pages. It seems to be the complete schematic diagram of a 6502, but it doesn't seem to be the original. It has markings about Atari 1985, I think, 1984, and it seems just re-engineered or something, or someone copied it by hand. It's missing a lot of the original meaning and interesting markings there. There's another one, a couple of pages. This one is not complete. Rockwell, 1982, handwritten. This looks more like the original because there's also corrections and everything. It's a lot more useful. But yeah, it's all not complete. But the question is, where would you look if you wanted to reverse engineer something properly? You wouldn't try to steal the source code or get the source code from somewhere. You would look at the actual thing, right? So people have done die shots of it, so this is a very early one, and everything people could understand about it was, well, there's some decoder, some logic, and registers. That's everything that was understood about that die shot. In 2001, some guy with the first name of Balázs from Hungary take really nice high-resolution photographs of a 6502 with some old Russian microscope, all black and white, but really great, and he did a lot of work reconstructing every single transistor and drawing this schematic diagram, which is complete and has every single transistor. And he did that all by himself and alone in Hungary, and then wrote a paper about it, all in Hungarian. And so some people, he was translated. Some people translated some parts of what he wrote and tried to understand, because I understood a lot about what was going on in the 6502 because of what he had learned from copying all those gates. But there were some other guys, Greg, Barry, Brian, and Ed, who just recently, so last year, they started about 1.5 years ago to do the whole thing again and properly and very high quality and debugging everything and making sure everything is completely correct. And these are the guys from the Visual 6502 project, which you have probably seen. So I'll tell you a little. So originally Ed was supposed to be here and do part of these slides, so I'll just show you what I understand about them. What he does, this would be far too dangerous for me, is they squirt hot sulfuric acid onto the chips to get the plastic off and to get to the actual chip. Sometimes it doesn't look that pretty, but they work. They can work if you clean them properly, and if you do it nicely, they can look like this. Let me show you some close-up here. So in this stage, they should actually still be working. And so just with a standard digital camera, you can get a resolution like this. And we have the 3 parts here already. By the way, what's important is the decoder is always on top. That's the correct orientation of a 6502. So if you look closely, was headed sideways. So as a next step, you need really high-resolution photographs of that, and you need some serious hardware for that, really good microscopes. What Greg did was take lots and lots of tiny photographs and then stitch them together. So one of these photographs would be this one. It looks all really nice. But just taking a photograph of just the surface wasn't enough, because that doesn't necessarily always show all the layers, because you can see all these layers, 3, 4, 5, 6, 7. There are many layers, and you cannot always distinguish those layers perfectly by just looking at it from the top. So as a second step, he also removed all the layers with some extra chemicals to get a shot like this. So this destroys the CPU, but yeah, it's for the greater good of being able to reconstruct it better. So after stitching, putting everything together, at the end he had a 200 or so megapixel picture, and it turned out 6,000 by 6,000 would have been enough for reconstructing everything. And he wrote some tool to basically draw the polygons, the original polygons of the traces on top of the pictures that he took. And so this is the first picture, this is the second picture, and so with his tool he drew the vias and drew the traces, and at the end you get all the traces just on top of that. And this would be the complete 6502 completely in vectors and redrawn. Of course, needs some debugging. So with these tools and with a lot of manpower, you get from this photograph to this completely digital and really nicely colored representation. So if you look at the intersections of all these traces and at what layers, at what levels they are, and understand NMOS and how this processing was done, from that you can derive the netlist. And the netlist is basically all the transistors and how the transistors are connected and how the nodes are connected to the transistors. And this netlist alone specifies the complete working of the CPU. So converting the netlist, so this is part 1 of the netlist, this is part 2, and these are the pull-up transistors. So all this, it's about 7 kilobytes of entropy, is everything that is needed to describe the 6502. So instead of trying to understand that now from some diagrams or something, the best thing is to simulate it and look at what's going on. The question is, how would you simulate all that? You simulate all of physics. So if you have on the outside, you can change pins. For example, you toggle the clock switch. And then you have to look at all the nodes that are going from there to all the transistors. And you have to look at what the potential of these nodes is, and they have to share all the same potential. And from there, so you look at all of them, you look at the group value, the potential of the group, and you set all the new nodes to the new potential, and then you look at all the transistors that are connected to all these nodes, and you need to switch some of those transistors. And then you look at all the nodes behind those transistors and repeat all that. And if you repeat that long enough, the system will stabilize, and all the nodes will have some fixed potential, and then you're in the next stage, and then you can flip clock again, and then you're in the next cycle. This is, of course, very slow, but it has some really nice properties. So normally, if you write an emulator, first an emulator would be you write it. It's not the original code. It's just a copy. It's just a re-implementation. The thing here is you don't really, if you need to get it more complete, you need to add a little more of data, but a lot more of code. It gets a lot more complex in code. If you do this with this netlist approach, the emulator, which emulates physics, is always the same. It's just a couple of hundred lines of code. And you just add more polygons. You just add more data. So with an emulator like that, you can emulate a 6502 or any other CPU done in the same process, or it doesn't even have to be a CPU. So I told you it was pretty slow. What do you do if you want to get something even slower? You write it in JavaScript. So here's the whole HTML5 goodness of the visual 6502 simulator that those guys did. I wasn't involved in that. You can see that it's all the blinking is the clock counting up and all the different traces changing their potential. You can see on the right how the clock is counting up, and you can see it's about 2-3 hertz. And this is the maximum speed you can get. So it's about 1 million times slower than a real chip. But you can zoom in, you can look at all these things. And there's even an advanced mode. In advanced mode, I've turned off the image now. If you run it, you can look at a lot of the internals, a lot of the internal lines, what's going on there, which component is outputting what. So this helps so much in understanding what's going on in these interesting edge cases. But speaking about simulation, and speaking about being slow, of course, if you rewrite it in C, maybe we can get it a little faster. So this is where I come in, and I wrote a C version of this thing. Looks a little like that. And if you run it, so in this small demo, you'll see I run the C version, and I feed it with the Microsoft Basic from the C64. Takes a while. Now it's counting the memory, how many bytes it has. This many? Okay. Yep. So 7 seconds. Normally it's a couple of milliseconds. So it's still 1,000 times slower. But we're getting there. We're still thinking about how else we could make it faster. So all these tools are really nice about understanding stuff. For example, we can automate something like testing through all the opcodes. What do they do? Which registers do they change? Which inputs, which outputs, how long do they take? We can measure all this completely automatically without using real hardware because we have completely perfectly simulated hardware. We can also do some interesting tests like break transistors and see whether the code still works. And you can break a lot of transistors, so this means that our code just doesn't do everything, that just doesn't exercise all the transistors. Or another thing you could do with it is, sure, you can use it in an emulator, but that's too slow. What you can do though is, if you look at how many emulators there exist, for example, this is the list, just a collection of NES emulators out there. And probably everyone has written a 6502 core for these, and there were, how many? 4 people here who have written 6502 cores. And these always have bugs. There are always weird edge cases, side cases that aren't handled properly. And with this perfect emulator now, you can run them side by side, and you can use the one to test the other, which is really nice. So what have we learned from all this? What can we now understand about what's going on inside the CPU? Part 3, from the inside out. For everything here, we have to start with this really nice schematic diagram again. Let's look at it a little more detail now. Program counter, that's not all that interesting. Sequencer and decoder, this is where the actual personality of the 6502 comes from. The rest is pretty standard. The whole arithmetic and logic is done like in any other CPU. You have the registers here, and the stack pointer, and the status register again. And the two buses, so the S bus on the left is connected more to A and the ALU, and the S bus is more connected to the indexing part of the system. Let's start at where instruction decoding starts, or first let's start with the timing generator. If you look at a trace, what's going on if you run code, you can see there's a lot of interleaving going on there. One instruction is still not finished, but the next one is fetched already. This is very much in contrast to something like the Z80, where everything is divisible by 4 cycles. It always has its 4 cycles, and then, okay, next instruction, 4 cycle, 1, 2, 3, 4. Here we have a lot of interleaving, so it's very memory bound. It's very fast per cycle. So in this example, where you can see here, the jump to subroutine is not even finished, but we are in T0 in the first stage of the next instruction fetch already. Here we are in the decode of the INX instruction. Here we execute the INX instruction, but we've already fetched the DEY instruction, which is the next one. So there's quite some interleaving going on there. Not in this case though, if you look here, because the INC instruction has to write back out into memory in its last cycle, so we cannot fetch the next one at the same time already. So because memory is already used, so you don't have overlapping here. So this is done really, really efficiently. So timing generator, next piece is the Decoder ROM. The Decoder ROM is, you can easily see that thing on this. It's the upper piece, the ROM. This is the big decoder. It has 21 inputs. It's really just a ROM. It's 21 inputs and 130 outputs. And the way it works is the inputs are the instruction register, which is the opcode. For example, A9 for LDA, and T, which is the cycle in which we are inside the instruction. And depending on the opcode and the cycle, some of these lines will fire. And it's not always just one line. It can be any number of lines. So for example, in these 4 lines will fire. So the Decoder ROM, this is the complete Decoder ROM. Let's look at the first ones in a little more close-up. The Decoder ROM compares the opcode and T, as I said, but it only looks at the upper 6 bits of the opcode. The lowest 2 bits just ignores, because what it actually looks at is this G value. I'll tell you about what G is on the next slide. For now, just assume it's a part of the opcode. And at time. So there's always X's, meaning don't care. So the first one would match to anything that starts with 1, 0, 0, and then has a 1 at the other bit, and would match in any of the clock cycles of any instruction that has this mask. So this G calculation, this is the rule for G, how G works. G1, G2, G3 are 3 separate lines which go into the Decoder ROM. And so this is a truth table for it, or more useful would be this table. So 0, 0, 0, 0, 1, 1, 0, and 1, 1 correspond to G values of G3, G1, G2, and the 1, 1 case, that's undefined, that's not used for the 6502. Or how you can interpret this is that G actually encodes which register we're working on. So the lowest 2 bits is it A, is it X, is it Y, for certain instructions. Others don't care about registers, so they don't care about the G, so it's a don't care, it's an X there. And you can see this in the opcode table. The columns 0, 4, 8, C, and 0, 4, 8, and C are the ones that mostly deal with Y. All the ones that deal with Y are typically in those. And then the next column is all about A, and the other one is all about X. So it's all about the lowest 2 bits. Yep, and here's another short video of the Decoder ROM in action. You can see that all the pink lines, these are the lines that are firing in all the cycles. Let's walk real quick through an LDA and an LDX, what the Decoder ROM outputs. LDA and LDX are encoded very similarly. So the only difference is the G value that they have. So in clock cycles 1, 2, 3, they do exactly the same. They have the same PLA, so Decoder ROM, PLA ROM outputs. But in cycle number 4, this is where the difference is. The one outputs something about A, the other one does something about X. So this is where they are different. So moving on from the Decoder ROM to random control logic. So Decoder ROM only does the front end for decoding, and random control logic is the back end for decoding. It takes as an input the 130 bits from the first stage, and what it outputs is, as you can see in this close-up, hopefully, yep. These are all control lines which go directly into some of the components, like the ALU or the buses. So this is very, very specific in controlling exactly what's going on. And let's look at this one example of connecting SB to X and connecting X to SB. This is the S bus, and X is connected to it, and you can either say, let's load from the S bus into X, or you can say, put the value of X onto the S bus, and these two control lines control whether this is the case. So this random control logic, I don't know where the name comes from, maybe because it's really that random, it looks random. We haven't found anything that makes it any easier to understand what it's doing. But let's look at the output of it, for example. So here's the output of an increment X with the PLA ROM and the random control logic in the first cycle and the second cycle. Now, let's look at this on the schematic diagram. In the first cycle, an increment X has to get the information out of the X register onto the S bus, and it puts it into the A input of the ALU. What it also has to put into the ALU is a 1 on the other side to add it. It does it by putting a 0 in there, by asserting this line, and adding a carry of 1, and saying, yeah, we want a sum. So in the next cycle, we will have the result in the add or hold register on the right of the ALU. Then in the second cycle, we have to get the add or hold register output, put it onto the S bus with these two control lines, and we store it into X in there. There are a few more bogus junk control lines there to keep the ALU occupied, which are a side effect of how the way is encoded, everything is encoded, and the way don't care works. So this doesn't have any influence on what's actually going on. But there are two more lines that are asserted: the one that sets the 0 flag, and the other one that sets the negative flag from the output. So break, IRQ, NMI, and reset. That's an interesting one, how this is all sequenced, how this is done in the sequencer in the logic. So as you see again, these are the vectors on the top of the address space. It's all really similar what's going on here. An IRQ pushes a program counter, pushes the status register, and jumps over a certain vector. If you have a break instruction, software interrupt, it does the same thing, but puts the break bit onto the stack. An NMI does the same as an IRQ, but a different vector. And a reset only jumps over a vector, but that's not actually true, because a reset also does this exactly the same protocol. It pushes PC, pushes P, but nobody cares because you have a reset anyway, so this is not really known or useful or interesting. So if you look at the whole table of what's going on, this no in push PC and P in the reset line here is actually also a yes, so this is all rather orthogonal. This is always the same code that is running. And so this is the code again, so there's two fetches. There's the store of the PCH, store of PCL, store of P, fetching of the vector low, fetching of the vector high, and then the fetch of the new instruction. Now the question is, how can this be done for an interrupt? For a break instruction, that's easy because it's an instruction. It gets sequenced by the PLA ROM. But how do you do that about an interrupt? And the trick here is done in this box called the predecode logic. You can see that this has the interrupt and reset pins as inputs. What it does is, normally the instruction register, the opcode, is fed by the opcode that comes from the data bus. But there's also a 0 input, and there's the IRQ, NMI, and reset lines go in there. So whenever there's an IRQ, NMI, or a reset, then the instruction register is not loaded with the actual instruction, but with a 0. So what this does is it injects a 0 into the program stream. And the 0, you might remember, is the break instruction. So this is a really neat trick here, injecting a break instruction which does the whole sequence of what's going on, but afterwards it has to clean up and do the right vector and has to put the break flag properly and everything. So it has to cache that information somewhere, but the sequence is done with the break. But this is exactly where this bug came from. You remember the break bug? If you have a break and an IRQ happens at exactly the same time, the break will get ignored. And this is exactly because of this, because it injects a break for the IRQ, and then, well, it drops the break. Some other things that can be explained with extra knowledge that we gain from that is the RMW double store, which is actually already documented So the original documentation say there's a destroy memory cycle in there, because it was just a don't care. If we look at the PLA ROM outputs, we can see that there's an explicit. I mean, it's done that way. I guess they optimized something, so we don't understand why, but we can see where it's happening. So now this is illegal opcodes. These are the holy grail of all understanding the 6502, and I think we have made some progress there. What people have done so far is mostly, well, measure them and see what are they doing. And there were some theories about, yeah, they seem to combine the ones that are close to them, but now we can say a lot more about them. So the kill opcode, for example, all these, most of them that end in 2, they just halt the machine. Reset still works, but RQs and NMIs won't get delivered. What is happening here? We can see in the diagram, by looking at the timing generator, because the timing generator actually has an input from random control logic. Because at some point, the timing generator must know when to do the next fetch, when to go to T0 again. And random control logic knows that because it has all the information about, from the Decoder ROM indirectly, what state we are in, what instruction we are in, and it will tell it at some point, let's restart at T0. And this is exactly what's going wrong with kill. You have the state here on the left, and the state more detailed with 0, 1, 2, 3, 4 as 5 as bits. In the kill opcode, so we are in T1, so the 1 bit is set. T2, some random stuff happens. We don't care what's happening there. But what you can see is that the way the sequencer works, it shifts the 1 to the right. So it shifts it into T3, T4, T5, and nobody ever says, okay, do the next fetch. So it just shifts it out. And so we're now in no state, and nothing will ever match again. And we will never fetch the next instruction, so the next one will be just the same, and the machine is just wedged. So some are a little more helpful than kill, so if we make them lighter and darker depending on how useful they are, there's lots of knobs which can be rather easily explained by well, there are no PLA lines that match them, so they don't do much, but the timing is controlled by the one on the left or the one on the right, because there's a don't care somewhere. But some interesting ones that can be explained, especially because they are actually useful, is the SAX and the LAX ones. So you can see whenever there's a Y, AX, on the right you can see one that seems to combine A and X for storing and for loading. And this is because, well, I lied to you before, this undefined here is not actually undefined because of the way the G1 and the G2 is calculated. In this 1-1 case, this is actually the case of G1 and G2 at the same time. So the A case is correct and the X case is correct. So if we go through step by step for an LDA, LDX, and LAX, you will see that in the first instructions, well, the LDA and the LDX do the same anyway in T1, 2, 3. But in T4, the LDA does something with A, the other one does something with X, and LAX is just true for both. So this is the store into the register. So it stores it into A or it stores it into X at the same time because both of these control lines are set. So there's a lot more about illegal opcodes that can be explained that way by just looking at these traces. But that would require quite a lot of time, and there are even some that we're still looking at. So the question is there's a lot of people involved right now that are doing this reverse engineering on some mailing list and our internal wiki. So what is happening there is that we're still investigating a lot more of these things, understanding how some of them are unstable and how some other things work. So one thing that we have, some really interesting internal representation is, this is the mapping from the opcode to what comes out of the random control logic as the very last step. So you can rather easily look up what's going on the bus in every cycle of certain instructions. But we're not only investigating the 6502 by itself, but also the different 6502s that are out there. There are so many things to do. For example, does anyone recognize this chip? It has a tiny little, well, not so tiny, 6502 on the bottom right. Which you can see here, it looks exactly like a normal 6502. This is the CPU in the NES. So it has the normal, I guess, licensed version of a 6502 in there and some video and audio logic in the same chip. And there's some other versions of the 6502 as well. Looking at them and comparing them is can tell us a lot about whether they fixed bugs or something. So for example, very old versions had some bug still, was fixed in the standard 6502. Rockwell licensed it. We looked at it, it looks a little different. There's a shrink used in later Commodore computers. And there's, in the cost-reduced C64 and the C128, there's another shrink, the 85XX series. So looking at all these would be interesting. But why stop there? Why not look at other CPUs? We have really nice representation of a Z80, and people are looking into vectorizing it right now. 68,000, that thing is complex. That's 10 times as big as anything else. But yeah, people are vectorizing that one as well. Why not use a complete computer? Why not look, well, we have the 6502 already. Let's do the video controller, the audio controller, the I/O controllers. And then we could have a complete C64 in perfect simulation and test all the other emulators against it. This thing can only be done by distributing the work, because that would be way too much for one single person. And Ed is actually working on making his editor to work with more people. Another thing to be done is just the chips is not necessarily enough. Also X-raying the PCB is, then you have the full chip, then you have the full system. That's something that we're looking into. Or why simulate it in software if you can simulate it on an FPGA? So someone is also working on baking a 6502 onto real hardware again. And so that was it. If you want more information, on visual6502.org, we have all the chip images, all the information. We have a wiki. We have the JavaScript simulator that you know. The vectorization tool will be there shortly. 6502 Hackers is a mailing list with lots of great people. And it's closed right now. You can apply for membership. We're planning to open it. And of course, there is my blog. Thank you.
Thank you, Michael. Does anyone here has questions?
So we took some time over. So please, everyone who wants to leave the room, please do it quick. We have another lot of coming in here right now. We are out of schedule, so we only have 10 minutes to prepare the room for the next talk.
Ja, komm mal mit. Ja. Ja. Ich komme gleich noch.